mass spectroscopy, that would take a lot more time, but you should consider this only as a kind of an appetizer, an aperitif for some future lessons, and perhaps someday ESMRMB will sponsor a high resolution or in vitro metabolic NMR spectroscopy workshop, and there will be more time to talk about these things. So I will just address two different things. One thing is to present the methods that exist, and especially some reasons why you may be interested in doing ex vivo or in vitro metabolic NMR spectroscopy, either instead of in vivo techniques or in addition to in vivo techniques. And then I would like to give you some information concerning the differences that you have to expect when you look at the results of in vitro spectroscopic results and compare this with in vivo results. So very quick, just a few slides. Here there are a few important methods that exist. I'm not talking about 1 and 4. There are some special cases, but about 2 and 3, which is first the spectroscopy of excised tissue, tissue that you excise from an animal, and then you do the spectroscopy without further processing, basically, and tissue extracts. That means you perform a physicochemical procedure of tissue that finally results in metabolite solutions. And that, the latter method, can be done in just about in any tissue type, and you can see metabolites that you cannot see in more or less intact tissue, while method number 2 shows you only those metabolites as they are in vivo, as visible as they are in vivo. So, so here are a few rationales that I want to present why you might be interested in doing in vitro instead of in vivo. Well, the first is a practical rationale. There may be some special cases where spectra are not easy to obtain in vivo. For example, if you want to image or to take a spectrum from a tissue region in the brain close to an air-filled cavity, then you may have difficulties shimming this region, getting a homogeneous magnetic field, and so you may not be able to do spectroscopy in vivo, so you may take a biopsy and measure the spectra like that. Or a scientific rationale may be you want to exclude effects of anesthesia, so there are perhaps specific scientific projects where you have to absolutely exclude anesthesia, so you cannot do in vivo experiments, so you have to take a biopsy. But the most important and interesting rationale is here number 4, like a methodological rationale, namely in vitro you can dramatically increase the spectral resolution in your spectrum. That means you can identify and quantitate a lot more metabolites than in vivo. This is particularly true for tissue extracts where you generate solutions, and to a somewhat lesser extent this is true for high resolution magic angle spinning where you don't extract your tissue samples. So here, just to give you a comparison of what you can see, this is an in vivo spectrum. The upper spectrum at short echo time, a few milliseconds, the lower spectrum at long echo time, 140 milliseconds, about 4.7 Tesla. That's what you have to expect from a brain in vivo, a mouse brain. You see the number of peaks is not extremely impressive in this spectral region. So now if we look at one range a little bit further, what's between the two red vertical lines, if we forget about what's to the left and to the right, we can see in vivo, we see maybe 3.5 peaks, or maybe even 4.5, and if you increase the field, maybe 1 or 2 more peaks, but that's about it, what you get in this spectral region. If you look at exactly the same spectral region from a brain extract after having processed it, if you look here at the water-soluble metabolites, you get something like this. And this is exactly the same spectral region that is highlighted above. So you see there is a lot more peaks. If you count also the small peaks, it's over 90 peaks that you can distinguish here. And most of these peaks are extremely narrow. They're only almost like vertical lines here in this presentation. So it's a very good resolution. You see a lot of details. Just let's look at 2 regions. This region, for example, the right flank of the NAA peak. In vivo, you hardly see some broadening, a broad base of the NAA peak, basically, on the NAA flank or a shoulder. If you look at the same region here, this is the same green spectral region. You see a lot more peaks, GABA peaks, even an acetate peak. These are all peaks, details that you would not even suspect when you look at the in vivo spectrum. Another spectral region is here, the glutamine-glutamate region, which does not give a well-resolved peak in vivo. Here at long echo times it looks like that. That's not impressive either. Here, this is the same spectral region, the red box, with a lot more information. Peaks that go all the way down, mostly to the baseline, that are very narrow. And I have shown you, if you attended my presentation downstairs, I have shown you even more details, especially in this glutamate peak that you here see in the middle of this red box. So that's an extremely high resolution that, of course, you get only if you do a very careful and optimized procedure, starting from extracting the tissue all the way through spectroscopy and the evaluation of the spectrum. That means spectral processing. So that gives you a potential of detecting a lot more details than in vivo under optimized conditions. Here I can go through all these peaks, through all these spectra. In actually unprocessed magic angle spinning spectra, you get actually less detail. So I have to rush through a little bit. And so if you see this good resolution, you may come to the conclusion that in vitro MRS actually examines the same metabolites as we do in vivo MRS, but at a higher resolution. So is it really the same thing that we are observing? That's the question. Is this hypothesis right? Is this correct? I would say basically yes, but. And there is a number of points why there are differences between in vivo and in vitro spectra. And all these, the answer to this question is that, or the background is that tissue excision and extraction are invasive procedures, physical and chemical processes that actually alter tissue at different levels, macroscopic, cellular, and for extracts on the supramolecular, molecular, and molecular level. So alterations to due to tissue excision, you have first of all ischemia, because at the moment when you excise your tissue from the animal, you cut blood vessels, there is no blood flow anymore, immediately you have ischemia, no more blood circulation. A consequence of that is hypoxia. That's the first metabolite that is being used up, because at room temperature or even at body temperature immediately after excision, there is still metabolic activity going on, which means oxygen is being consumed, but no new oxygen is coming in because there is no blood circulation anymore. That has consequences. Upregulation of glycolytic processes. Aaron Terschap has explained a lot the glycolysis and oxidative phosphorylation, so I don't go into this. That means increased production of lactate, of lactic acid. That means under conditions of warm ischemia, namely where the tissue is still warm, you get especially decreased pH value because of lactic acid production. And since glycolysis cannot completely compensate for the ATP production that is usually provided by oxidative phosphorylation, you get rapidly also decrease in high energy metabolites like ATP and phosphocreatine. So these are one of the effects that you get in excised tissues, and of course you can limit these effects by optimized handling, but you cannot exclude them. And you should not be surprised if you get a huge lactate peak after tissue excision that you never saw in vivo. It's simply probably because of that. And those processes are pretty fast. You don't have to wait 5 minutes before you get high lactate. Within half a minute you can have it already and a very low ATP. So I think that is the first approach to this, and you may look up the slides in the book here. Thank you very much.
Thank you very much.